Hello, in today's lesson we will learn about the emission of alpha particles from the nucleus. This theory was first proposed by Gamow in 1928. Experiments of Rutherford on scattering of alpha particles by nuclei firmly established that Coulomb's inverse square law associated with the electric field around the electrically positive nucleus is maintained up to distances of order Rn. We know that in Rutherford scattering, some of the alpha particles were scattered exactly at 180 degree. So they just reversed their direction of velocity. And from that we know that the radius of the nucleus Rn is of the order of, we can calculate, is of the order of 1.2 multiplied by 10 to the power minus 15, and it depends on also the mass number of the nucleus. So this is roughly the length scale of a nucleus, of the radius of the nucleus. For the heavier nucleus, A will be the value of A will be large. For smaller nucleus, naturally it will be small. But within the nucleus, for values of R less than Rn, values of R less than Rn, from this figure we can see that this is Rn, 0 Rn for R, values of R in this region. Powerful attractive forces come into play which holds the nucleons together. The true mechanism responsible for nuclear forces is understood in the framework of quantum chromodynamics. But for our purposes it is sufficient to know that such nuclear forces must be capable of maintaining strong attractions between proton and neutron, proton and proton, neutron and neutron. If it were Coulomb's attraction, then proton and proton would have repelled each other. Proton and neutron couldn't have attracted each other because this is positively charged and this is chargeless, neutral, and these two are completely neutral. So we see the attraction between proton and neutron, proton and proton, neutron and neutron. This is a new form of interaction, and this is termed as nuclear binding force. Within the nucleus, for R less than Rn, the proton must have negative potential energy because it is prevented from escaping. So if the potential energy of the proton is negative, suppose this is V equal to 0 line, it's negative, then one has to supply some energy so that V0 becomes positive. That means the proton is bound within the nucleus. We can assume that it is negative, of course, but we can also assume for simplicity that V equal to minus V0, where V0 is a constant. So this line is parallel to the V equal to 0 line, but which is shifted downwards because the range of nuclear force is within the nucleus. So when Rn, at the point Rn, Coulomb's repulsion starts. Coulomb's repulsion means the alpha particle is repelled by the positively charged nucleus. So that is 1 by R potential. This is 1 by R potential. However, you see in this point potential has a discontinuity because this portion is not known how these two graphs are joined each other. So at Vm there is a discontinuity. But using this Coulomb potential, we can estimate what is the height of Vm, that is the height of this potential barrier. This is a potential barrier. Let us take uranium, A equal to 238, then Rn is 1.2 10 to the minus 15, 238 whole to the power 1/3 in meters. So Vm, which is a repulsive potential, is 2Ze square by Rn Rn is this we have just seen, and 2Z2 for the alpha particle charge 2. Z is uranium or uranium 92 E square in SI system 1.6 10 minus 19 coulomb, but we are using SI system, so 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught is 8.99 multiplied by 10 to the power 9, and these are the numbers. So this is 10 to the power minus 19 squared minus 38 plus 9 29, and 15 goes up, so 10 to the minus 14 in SI system, so it is joule, and all these numerical factors are in this place. We can simplify this, and then we get 569.44 into 10 to the power minus 14 joules. But 1 joule is 6.242 multiplied by 10 to the power 12 MeV. Much this many joules is about 35.5 MeV. The alpha particles which are penetrating this barrier, their energy can be measured. Most energetic alpha particles have energy of 4.2 MeV, which is much smaller than the height of the barrier. The barrier height is 9 times the energy of the alpha particle. So this is a question that classically a alpha particle which has energy 4.2 MeV cannot penetrate such a barrier which is so high, 35.54 MeV. So this has to be investigated in the framework of quantum mechanics. So in quantum mechanics there is a technique called WKB approximation, not exactly solving Schrödinger equation rigorously, but it is a semi-classical approximation. I have seen these very good discussions on WKB approximation in Griffith's quantum mechanics book chapter 8, and also in the internet by Barton Zwieback. This is a video lecture, and also the PDFs are available in the net, on the net. MIT Open Coursework. In this website you will find this video lecture and also the PDF notes. Extremely good, this both of them. I found them very helpful. So okay, so let us look at the Schrödinger equation. Del square psi del x square plus 2m by h cut square E minus v psi equal to 0. This is the barrier V, and this is the energy of the alpha particle. These are some fundamental constants. This is a second order differential equation, so we know how to solve it for certain potentials, for example fixed potential or harmonic oscillator potential or hydrogen atom potential. We know how to handle this equation in a mathematically rigorous way. Then in those cases what we find is that for various values of E called eigenvalues, we get various wave functions. So each eigenvalue has a wave function. So these are eigenvalues, these are eigenfunctions, and because this is time independent Schrödinger equation, these wave functions are those of the states which are not varying with time. So not varying with time, because this is time independent Schrödinger equation. Time part is e to the power I by h cross et, so that is just a phase. But let us concentrate on this equation. In WKB approximation, it is generally rewritten as del square psi del x square and px square by h cut square psi equal to 0, where px is a position dependent momentum. So this is exactly this. So there is no approximation from for going to this step to that step. Px is defined as plus minus root over 2m e minus v. So in the WKB approximation method, we try a trial solution psi equal to exponential I by h cut s. S is a function of x and e. Then this trial solution will be substituted here, and the value and the form of s can be determined. So that is the philosophy, that we guess a solution, substitute in the original equation, and try to see what are the unknown quantities in the trial solution. S is expanded in powers of h cut. So here, keeping the first two terms, you have s equal to s0 plus h cut s1 plus a higher order terms in h cut. That means if you substitute this here, then you get psi equal to exponential I by h cut s0 plus h cut s1. When we come from here to here, now this is approximate solution because we are neglecting the our higher order in h cut. H cut is very small, so still this is not exact. So when we substitute this into this and solve for s, then s0 we get plus minus px dx. Upper limit is x and lower limit is the starting point of this p. The potential can be broken into various pieces. So this from here, this px, the px, this is e minus v. The starting point is here. Depends on the problem under consideration, but the upper limit will be x. So x is the upper limit. So s0 is plus minus px dash dx dash, and s1 is I by 2 log of px. But this solution is valid under the validity condition of h bar multiplied by p dash by p square. The magnitude of this is much less than 1. So this you can find in both in Griffith and this lecture. You have to know that what is the validity of WKB approximation, that is h cut p bar by p square, magnitude much less than 1. This actually physics is that the potential varies very slowly compared to the, it should not vary much within the de Broglie wavelength of the particle. So within the de Broglie wavelength it should vary very slowly, but it can vary, but that variation, the scale of variation should be much larger than the de Broglie wavelength of the particle under consideration. So that is how that in that case WKB approximation will be a very valid approximation. So then if you substitute this s0 and s1 into this side, then you get psi equal to exponential I by h cross I by a plus minus I by h cross px dash dx dash. The first factor is because of here, first factor. The second factor is h cut cancels, and then I squared minus half is half in log px. So that is the second factor because of this, first factor because of this. This is e to the power something log, so this simplifies to 1 by root p. Psi becomes 1 by root p exponential plus minus I by h cut. Upper limit is x, px dash dx dash. This is a form of the solution of a WKB approximation wave function. So we haven't got a family of solutions like when we solve Schrodinger equation. We get family of solutions with various values of n, but here we have got in the lowest order in h cut, we have got a solution psi equal to this. So this is a semi-classical approximation, the lowest order in h cut. But notice that we have to substitute this px dash, of course. If we substitute px dash, then we get this v is larger than e. So that means this is a negative quantity. So we get a I here, that is we get a minus sign. So this solution exponentially decays. If we took the other sign, that is minus sign, suppose we took minus sign, then this I and the I here would have given me a minus plus. So this would have been a solution which is exponentially growing, but because we are tunneling a barrier, the probability is falling as we are proceeding in the direction outer. know that this minus solution now is we are not taking, we are taking the plus solution. Why? Because there is a I coming from here, so I minus, and this becomes exponentially decaying solution. But for the tunneling, because in tunneling the probability is decreasing as we are going far away from the nucleus. So let us see a little bit about what is the tunneling of alpha particles. If an alpha particle is ejected by a nucleus of mass number a plus 4 and atomic number z plus 2 with energy E, then the daughter nucleus will have a mass number a and atomic number z. If there are n nuclei at time t, then the transformation constant lambda defined by dn dt equal to minus lambda n. So that means we know that dn by n equal to minus lambda dt, so log n equal to minus log n equal to minus lambda t, so n equal to e to the power n0 e to the power minus lambda t. So we know this. This is the transformation constant, sometimes called disintegration constant. So this is lambda. But if P is the probability that the alpha particle penetrates the barrier, now we have come to the barrier penetration. So if P is the probability that the alpha particle is penetrating this barrier, then lambda has the expression V by 2 Rn multiplied by P. So this is the P of tunneling. P of tunneling. Not this P and this P is different. This is position dependent momentum, but this is probability. So we have to keep that in mind. Okay, so what is this factor? I have just highlighted it just for fun because let us check the dimension. So V is a length by time, and this is length. So this is dimension 1 by time. This factor 1 by time. So that is this is the average velocity of the alpha particle within the barrier. This is the radius of the barrier. So 2Rn is the diameter of the barrier. So that means this is the inverse of the average time. The alpha particle is coming from here to here to here to here, oscillating from this place, turning points, oscillating, and this is the average time, inverse of the average time of the collision between the two sides of the potential well. Right. So that is the inverse of the average time multiplied by the probability, that is the disintegration constant. So if we took the log of this, that is log lambda equal to, this is roughly a constant, so that is log C0 plus log P. We will use this equation later when we will find lambda, when we will find P, then we will use this equation. So keep this in mind to find the lambda. Now let us see a little bit closely what is this P. P is the probability of barrier penetration. We know another probability in quantum mechanics. Suppose we have a wave function like this, then the probability of finding the particle in a specific space place is psi mod square, right? So this if we want to find the probability of finding a particle, suppose here, then we will do mod psi square here. If we want to do here, then mod psi square here. So the particle can be anywhere quantum mechanically, but with a probability associated with that point in space. So how so this penetration, if we want penetration, that means the particle is here, and then what is the probability of particle is there. So that is a semi-classical approach. Okay, so in the semi-classical approach, let us take then we see that let us consider the particle can be either here or here. So this is A or B. So probability of finding the particle here is, suppose we have n0 experiments. So that means n0 psi a mod square, that is the number of times the particle will be found here. and number of times the particle will be found here is n0 multiplied by psi b mod square. Then the probability of finding the particle at B, given that the probability of finding the particle at A is mod psi a square, that is what we want. So that is n0 psi b square divided by total number of cases, so n0 psi a square plus psi b square. But because it is tunneling, psi b square will be much less than psi a square. That is the physics. Psi a square much greater than psi b square. That means n0 cancels, so psi b square by psi a square. That is psi b by psi a whole square. So that is our p in the semi-classical approximation. So we will try to find this p, and we know the wave function, form of the wave function here. So now it is clear what we are going to do. What we'll do is that we have found this p equal to psi a square by psi b square. We have found what is psi in the WKB approximation. So we will try to know what is psi a and psi b from this expression, using this expression. Then we will get divide them to get p, and if we take the log p, then we can substitute here. Then we will get a handle on the alpha disintegration constant, which can be measured in an experiment. So this is the experimentally measured quantity. So all this we have to do. We have to take the probability, then we have to take a WKB theory, which is a very microscopic theory, right? Theory of quantum mechanical theory, which is valid at the length scale of an atom. And the experiment is macroscopic. So there is a detector and there is a sample, and these two things has to be tallied. How will you do that? Then there is the probability of p, then calculate the probability p using the microscopic theory, then take the log of that, and then calculate lambda, and lambda can be measured in an experiment which is macroscopic. So there are these two things, microscopic theory and macroscopic experimental setup. So from the definition of psi given in equation 7, what is equation 7? This is the equation 7. Now we can write down psi a squared is x0 to a, and we have seen that this is imaginary, so there is I, so this is a real thing, so this exponent is real. So when you square, you get a 2, that is c square by e minus v exponential 2i of this. You know what is this? Because it is real, we have squared. Because if it were imaginary, then we would have got just the amplitude square. But here it is imaginary. Inside the barrier, v is more than e. That is, this factor is negative. Psi b square similarly is x0 to b. Again we get the same thing, c square by e minus b exponential of this. That is probability p. This is neither momentum, this is not momentum, so this is probability. So that's why I have written not momentum. So here this amplitude is not there anymore. So exponential 2i a to b 2m by h cut square e minus b to the power half dx. This is x0 to b, this is x0 to a in the ratio e to the power x by e to the power y, in this ratio e to the power x minus y. So x0 to b minus x0 to a, this limit cancels because of this minus sign. Then we have a to b, that is when we find p, then we have to put the limits a to b. Then the probability p of finding the alpha particle at a distance r, so this is our potential at a distance r within the barrier starting from Rn at a distance r. From Rn is Rn to r, 2i 2m by h cut square e minus v dr. If we take the log of p, then log p equal to exponential goes 2i. This is the integral which we have to do. This is the integral. So now the problem is well defined. We have set up an integration. We have to do it to get log p. Then we use the log p here to get the disintegration constant, and then that disintegration constant is to be compared with theoretical experimental observations. So you see this expression, let us look at it closely. So this is the Coulomb term, and we know that the Coulomb term in SI system and CGS system looks different because there is a 4 pi epsilon naught in the SI system. But I want to do this integration in a simple way, so we can use the CGS units. Using the units will not change the physics. So at the end, the physics that we will get by using CGS units or SI units is the same. And I will also tell you how to do it in the SI units after I finish my integration. Okay, so in CGS units, this is 2z is square by r. We have to simplify. We have to do a change of variable. What is the change of variable? Change of variable is this r is r1 cos square theta. So we are changing from r to theta. R1 is fixed. R1 is fixed, where the energy is it is going out of the barrier. That is dr is r1. This is 2 cos theta minus sin theta d theta. So this is the expression of dr that we have to substitute here. Then the integrand itself. Integrand is e minus vr. If we substitute e equal to 2z is square by r1, that is r1 downstairs, r1 cos square theta, that is e sec square theta, because there is a 1 by half. So I e to the power half tan theta. Okay, what about the limits Rn and R1? Rn is here is n, there is n, so that is theta n, and R1 there is 1, there is 1, so our R1 cancels, then theta 1 is 0. So Rn to R1 is theta n to 0 for R1. R1 is R1 cos square theta 1. So R1 equal to R1 cos square theta 1, so R1 cancels. That means cos square theta is 1. So theta 1 equal to 0. So that is Rn, R1 has to be replaced by theta n 0. So that is theta n 0. Okay, so here I have written down the integral once again. So this is the integrand and this is the dr. Let us see, I gives a minus, this minus, so this minus will go, then r1 to the power 1 by half r1, so that will give r1 to the power half, z to the power half, 2 to the power half twice, so that will give it 2, so 2, 4 by h cut, 2m to the power half, 2z e, let us take e out, the r1 of course has gone, and tan theta is here, tan theta is sine by cos, so cos goes, so that means sine square theta d theta, 2 to the power half, 2 to the power half multiplied by 4, this is 8, so 8 by h cross mz r1 to the power half is theta into the power to 0 sine square theta d theta, and sine square theta d theta is half of 1 minus cos 2 theta d theta. Okay, good. Then this 2 and 8 becomes 4 by h cut. 4 by h cut is mz r1 to the power half e. So that is theta n to 0, 1 minus cos 2 theta d theta. This gives minus theta n because this is lower limit. This gives plus sine 2 theta n by 2. Take one again, let us remove this minus sign and remove this half. So the minus sign goes here, and I want to also remove this factor of half. So take one of from 4 we take 2. This is 2 theta n minus sine 2 theta n. That is log p is minus 2 by h cut mz r1 to the power half e pi minus this and this. I'll tell you how to substitute theta n back to r again. So let us start from this equation, r equal to r1 cos square theta. So that means cos square theta n is rn by r1. Now rn by r1, we can see the picture. Rn by r1, this is much less than 1. The cos theta n is root over rn by r1, that is theta n is cos inverse root over rn by r1, and this is pi by 2 minus root rn by r1, because you can expand sine inverse x as x plus half x cubed by 3, and sine inverse x plus cos inverse x is pi by 2. So cos inverse x is pi by 2 minus sine inverse x, which is pi by 2 minus x, neglecting x cube. And sine 2 theta n multiplied this by 2, that is sine 90 minus 2 root rn minus r1, so that is 2 root rn by r1. So this is 2 root rn by r1 with a minus sign. This is pi minus 2 root rn by r1, so the root e factor in log p. Okay, now suppose you can ask, now suppose we can use the SI systems here, then there is a 4 pi epsilon naught, then we can redefine e square as e by root over 4 pi epsilon naught, and this constant will go through the integration, and finally here, let us say here we will substitute e by root over 4 pi epsilon naught. So that will be the expression in SI system. And also again you can say that I don't want to do that trick, I want to keep 4 pi epsilon naught here. Okay, that is also fine. So if there is 4 pi epsilon naught here, 4 pi epsilon naught here, 4 pi epsilon naught, 4 pi epsilon naught here, 4 pi epsilon naught here, then when we substitute the value of e, then we get 4 pi epsilon naught. That will go out of the integration. So there is a root over 4 pi epsilon naught, there is a root over 4 pi epsilon naught, root over 4 pi epsilon naught, that will come all the way to here, root over epsilon 4 pi epsilon naught. So this if you want to use CGS units, which is now nobody uses CGS units, then this expression is perfectly alright. But if you want to use a SI system, then put a root over 4 pi epsilon naught here, then you can use all these quantities m, e, r all in SI units, which is convenient, right? Okay. So that means log p is has one factor, which is 1 by root e, the first factor, and the second factor has 1 by root e multiplied by 1 by root r1. So root r1 is again proportional, r1 is proportional to z by e, y z by e, r1 is 2z e square by e, z by e. That means root over r1 is proportional to root over z by e. So root e goes upstairs, root z downstairs, root e is cancelled, and this is z because z square to the power half, then 1 root z, so there is z to the power half. And this is this log c0 that we had in when we were discussing in the first transparency. second transparency. This is the log C0. Okay. So this we have reached up to this, where log lambda is related with the energy of the alpha particle and its value of z. That is the value of the atomic number. So this is 1 by this is z to the power half term. That is z term. Z term has 1 by root e, and then there is constant term. This can be put directly in a computer now and checked. Its validity can be checked with the experiment. So that is so this is a perfect place to stop this lecture. But we want to discuss a little bit about the Geiger-Natal law. So that is why I have one more transparency. So this is the modern version of Geiger-Natal law, C plus D e to the power minus half, and this is the old version of Geiger-Natal law, A plus B log R. R is a range, but range and velocity is related by Geiger's law. This is the reference. So old version of Geiger's law, log lambda becomes A plus B log V. So there is a log V dependence with log lambda. But modern version of Geiger's law, e to the power minus half, because it is kinetic energy 1 by V. So there is a difference between the modern version and the old version. Why in 1910 they thought that it is a log V? Because if we plot log x and 1 by x, this is 1 by x. You know this constant can be negative, so I have plotted minus 1 by x. Then they for certain ranges their shape is very much same, and also you don't have the data for the whole range. You have the data only for a small window, that is a 208 to 238. For that the velocity is calculated as this to this, 1.4 into 10 to the power minus 9 centimeter per second to 2 into 10 to the power 9 centimeter per second. So that is log V is between 21.05 and 21.41. So we have information on this small window. From that having part of the data, it's a partial data. So from that it was very difficult at that time to decipher the difference between 1 by x and log x. So Geiger-Natal law was this, but from using quantum theory, Gamow showed that this is 1 by V. So this is the modern form of Geiger-Natal law. We should keep in mind that accuracy of experimental result increases as time goes. Alright. So in 1911 the accuracy of the experimental data was much less than what you would expect at the moment. This is a page from my book of Yarud, the Atomic Physics Yarud Volume 2. You can see Hans Geiger and John Michel Natal, they plotted log lambda with log r, and they got straight lines. And they found that the relation is between log lambda and log r is straight lines. So they wrote log lambda equal to a plus b log r. Anybody will say that it is the log r and log lambda. I mean, I would also say the same thing. That is a plus b r. But the point is that we have the data in a small window, not for the whole range. So it can be deceptive. Appearance can be deceptive, right? So this is an empirical relation based on experience rather than theory. So that is what Gamow did. He saw that there is an empirical relation, and then he used quantum theory and found the theoretical relation. This is the theoretical relation. and unfortunately Gamow never got Nobel Prize for this work, though it is a very fundamental work. But unfortunately, but this happens because we know that S.N. Bose has also not got Nobel Prize but though he discovered the Bose-Einstein statistics. Then we know that Sommerfeld, so many students got Nobel Prize, but Sommerfeld didn't get the Nobel Prize. So this is something which is beyond physics and these selections. So we are physicists, so we should be happy with the physics that we do. And that is the end of story. So let us. So that is our discussions on the emission of alpha particles. So now we can stop our discussion here, and thank you for watching.